Hello, my name is Jeremy Randall, and I'm going to be explaining my topic 5 through 12 on this final project. Alright, the first problem consists of a pump that has a diameter of 0.18 centimeters and a length of 13 meters. Sludge flows through the pipe at a velocity of 0.3 meters per second, and the pump has contents of commercial steel. Calculate the pressure drop and head loss in the pump, assuming the density of sludge to be 1440, and then calculate the head loss and pressure drop, assuming the new velocity is 60 meters per second. Right away, it's talking about calculating head loss and pressure drop, so that's Bernoulli and Reynolds number, involving internal flow, which is laminar and turbulent. Right away, the equations that are going to be present are the Reynolds number, the friction factor, the head loss equation, and then the pressure drop equation. We know Reynolds number is density times diameter times volume all over viscosity. Friction factor is based off its laminar or turbulent, has two different equations. And then head loss is your delta pressure over rho times g, which is known as 4 times the friction factor over length times diameter over velocity squared over 2 times gravity. Right away, we assumptions were steady state, sludge values were given, the pipe is commercial steel, and no valves or bends are in the system, fully compressed flow. We also found that the roughness is 0.045 millimeters from table A12. Right away, we can calculate the Reynolds number using all the knowns, the density, diameter, volume, viscosity, to get 58, which is laminar. With the friction factor, that's 16 over Reynolds number, we get 0.276. When we plug that friction factor in and all these other knowns, we get a head loss of 36.56 meters. Then, when you manipulate that head loss equation to calculate for delta PL, you just multiply your friction factor times your density times gravity, which gives you 516.6 kPa when your velocity is 0.3 meters per second. Next, when your velocity is 60 meters per second, you get 11,600 as your Reynolds number, which equals turbulent. Right away, you solve for your friction factor known as turbulent, and that is another equation, this 0.001375 factor. We know the roughness was given, found from that table, A12, which is 0.045 millimeters, so we get a friction factor of 9.37, and then once again calculating head loss to be 4.96 times 10 to the 7 meters, and then a pressure drop of 6.8 times 10 to the 8 kPa, which is drastically different with the increased velocity. Next problem is liquid being pumped out of a reservoir at a certain volumetric flow rate. The reservoir is flowed with water at 55 degrees Celsius, and assume the head loss between tank and pump is 12 and the net positive suction head required is 20 feet. Using your knowledge on cavitation, calculate the minimum outlet pressure. Right away, it's talking about calculation and net positive suction head, so I know this is pump analysis. We know that when cavitation is before it occurs, we know that the net positive suction head equals the net positive suction head required, and that makes the P2 min equal our pressure suction. We also are given a head loss of 12, and then we could calculate a PSAT at 55 degrees Celsius, which is 15.76 kPa. With all that in mind, we could calculate for area, volume, velocity, and our friction factor. And then when you substitute the net positive suction head required into your net positive suction head equation, you can solve for P2 min. And finally, you get P2 min is 44.04 kPa. Next, you have oil and natural gas are usually found in pores in deep rocks. They are extracted by pushing a high pressure fluid through rocks where the oil is displaced from the pores. Find the minimum fluidization velocity of water and air through the rock. In this scenario, treat the rock particles as if they are loose and positioned vertically as the picture shows. Right away, we know this is porous meter as it's flowing through porous rock, and it's calculating the minimum fluidization velocity. And based off the assumptions present, we can treat it right because the rock particles are loose and positioned vertically. The equations that are going to be present is the minimum fluidization velocity equation, and when we set that equal to 0, we can calculate for the velocity for each component. And we know the water density, we know air's density, and then we start solving for it. So with this equation, you break it down into components A, B, C, and when you calculate that, you get water's minimum fluidization velocity to get 5.7 times 10 to the negative 5 feet per second, and then you get air's minimum fluidization fluid to velocity to be 5.6 times 10 to the negative 3 feet per second, which is greater than the water's fluidization velocity. Next, we have a question that asks to find the terminal velocity of a particle settling under gravity given the weight force equals the mass and buoyant force, and the mass isn't changing. use momentum balances in the given information. Right away, we ask for the terminal velocity of a particle, which is particle separation, so I'm assuming this is external fluid flow. The density of fluid is given, the density of particle is given, so also the drag coefficient and the diameter of particle. So in this problem, we're going to be using the momentum balance equation, we're going to be using the drag force equation, and then the drag coefficient equation all together. So right away we could cancel. We know that mass doesn't change, so dm dt goes to 0. So we say sum of force equals mdv dt. The sum of the forces was weight minus the drag force. The weight is the weight. It includes the weight of the particle and the buoyant force, which is present right here, and then the drag force. With all that in mind, we can factor out the volume and get just our densities, and then we could factor out a volume multiplied by density to get a mass on the right side. When terminal velocity is when dv dt equals 0. So when you calculate that, you get your drag force equals 4/3 pi diameter over 2 cubed times your density of the particle minus density of fluid times g. We know the drag coefficient is your drag force divided by the area projected over half of the rho times velocity. So when you substitute this drag coefficient into the drag force, or drag force into the drag coefficient, you can solve for terminal velocity, which you get 5.02 times 10 to the negative 11 meters per second. Next, the problem consists of a rocket that requires a large amount of energy and thrust to move upwards. Convergent divergent nozzles can be really useful in rockets. Air enters this convergent divergent nozzle in a rocket with negligible velocity and a pressure of 1500 kPa. Determine the lowest pressure that could be observed at the throttle nozzle. Right away, it mentions convergent divergent nozzles, so I'm assuming this is compressible flow. The equations that are going to be present are the critical pressure, which is when Mach equals 1, and this critical pressure is given by the initial pressure times 2 over K plus 1, all raised to the power of K divided by K minus 1. The assumptions is Cp is constant for air is ideal gas, and the flow through the nozzle is steady and isentropic. The value of K is found from table A1 to be 1.4. So with all that in mind, we can say that when there is negligible velocity, stagnation pressure is now equal to the inlet pressures, which is 1500 kPa. So now plugging that into this critical pressure, we get a value of 792.4 kPa. Lastly, a problem consists of an incompressible Newtonian fluid which is flowing downwards between two wide parallel plates in the y direction. The flow is treated as a steady state with no slip at the walls and laminar. Using handout 9, figure C3, calculate the velocity field using your knowledge of Navier-Stokes and equations gained from fluid mechanics. Right away, it mentions Navier-Stokes, so I'm assuming this is Navier-Stokes boundary condition and microscopic mass and momentum balances. So in this picture, you see we got two wide plates in the y direction, and velocity is going downwards y. So we know that the velocity in the y direction is not equal to 0, but the velocity in x and z direction is equal to 0. So when we use the continuity in the correct coordinates, which is rectangular, we get the change in density over time equals change in volume of x direction over dx, plus change in volume or velocity in the y direction over dy, plus change in velocity in z direction of dz. dvx dx and dvz dz go to 0 because there is no velocity in there. So now we know that the change in velocity in y equals 0 based off the continuity. Now when we do the y momentum balance, we write that all out, and now we start crossing out all these assumptions that were present. We knew that their flow was parallel, incompressible fluid, Newtonian, and laminar, and we knew there was no slip at walls. So we know that Vx and Vz equals 0, so all those Vx, Vz cancel out. We know it's steady state, so Vy, dVy, dt goes to 0. And then we know that there's no pressure change, so delta P equals 0. And then we know that Vy, dVy, dy is 0. So with all that in mind, we could calculate that your density times gravity times your density times gravity divided by viscosity is equal to the second derivative of your velocity y in the respect to the x. When you integrate this 2 times, you come up with the equation density times gravity times x squared over 2 mu plus c1x plus c2. Using the boundary conditions, you calculate for c1 and c2, and lastly you get a value for your velocity, which is your velocity profile, which is density times gravity divided by 2 mu all times x squared minus h squared divided by 4 in parentheses. Thank you.